Okay, welcome back. This is section 4.3. We're going to talk about root and operations with radical expressions. Specifically in this video, we're going to use calculator approximations, simplify radical expressions, add, subtract, multiply, and divide radical expressions, as well as rewrite some algebraic radical expressions using factoring techniques and simplifying expressions. Okay, so if you are not familiar with all of the properties of exponents, please go and practice a little bit more and then come back to us. Just to make sure everybody's on board, go ahead and do these 9 problems. Pause the video. Okay, welcome back. Here are the answers. Please pause the video and check your work. If you get more than 3 incorrect, please go ahead and practice a little bit more and then come back to us. Okay, so up until this point, this is the square root of x, and that's the radical sign, and then we have the radicand. And so you wondered why it wasn't called the square root sign. Well, it's not called the square root sign because technically there's a little n there that we call the index. We just don't write it for square roots. So if we have x squared and we want to undo that, we take the square root. And so that's positive or negative x. And we don't need to write that little 2 there. However, if it's x cubed, how do we undo that? Well, we can take the cube root of x. And so, of course, that's x. And so this right here, this 3, is what we call the index. And that tells us what root we're taking. We can, of course, do that for x to the 4th. And so we can take the 4th root. And then, again, it's positive or negative x. And we can do the same thing with x to the 5th and take the 5th root. And then, of course, that's x. So you notice that I put positive and negative on some of them and not on others. And that's because if n is odd, we only have one possible outcome. So we're only going to have one real nth root. However, if n is even, we have this issue because negative 5 squared equals 25, which is the same thing as positive 5 squared. And so we have this principal root, and that's the positive form of it. And then we also have a negative root. And so that is the negative form that also gives us the same radicand. And of course, if b is negative, there are no nth roots, no real nth roots. Okay, so this comes from, again, if we have the square root of 25, that's 5. That's the principal square root. That's what you'll get out of the calculator. However, we could also have a negative principal root, the opposite of the principal root. So the negative square root of 25 is negative 5. So we, in general, when we're talking about square roots, make sure that we are making accommodations for both the positive and negative principal roots. So, for example, in part A, we have an odd index, it's 3. So we know we only have one real root, and so we can rewrite this as the cube root of negative 2 cubed, because negative 2 cubed is negative 8, and so our answer is negative 2. And then we can go over here, and in our calculator we can do the square root of 400ths, and we'll get out 2/10. Well, 2/10 is only the positive principal root. There's also a negative root that if you multiplied 2/10 times negative 2/10, you would get positive 400ths. Okay, go ahead and try this. Welcome back. Here are the answers. Go ahead and pause those if you want to take a look at them, and we're moving on. Okay, so how do we deal with this when we have exponents? Well, if n is odd, then we have no problems. If n is even, however, we want to force a to be positive, so that way we're talking about only the principal root and not both roots, and it becomes a little less confusing. So the 4th root of y to the 4th, normally we would say y, but because y could be positive or negative, we're going to force y to be positive by using the absolute value sign. That's going to be the same thing over here. So if we have the 6th root of 64, which 64 is 2 to the 6th, and then we have x squared minus 3 raised to the 16th, so we can rewrite that as x squared minus 3 raised to the 3 times 6. And now we can simplify. So the 6th root of 2 to the 6th is just 2. And the 6th root of x squared minus 3 quantity to the 3rd times 3. part of that comes out, so we end up with x squared minus 3 quantity squared. Now, we know that this, even if this is negative, what's in here, this is going to be squared. And so that's going to force that to be positive. So we don't actually need the absolute value sign there. Okay, go ahead and try those. Pause the video. Welcome back. Here are your answers, and we'll move on. Okay, so we can also simplify radicals when they're not under the exact same radical sign, as long as the indexes are the same. So for example, in part A here, you'll notice that this is the cube root of 8 plus the square root of 2. They have two different indexes, so we cannot combine them. Here we notice that the indexes are the same, so we can combine them. So we're going to rewrite this as the cube root of negative 4 times 2. And so the cube root of negative 4 times 2 is going to be the cube root of 8. And the cube root of negative 8 is negative 2. Okay, go ahead and try those. Pause when you're ready and come back. Okay. Welcome back. Here are the answers. Go ahead and pause the video so you can review those. Okay, we can simplify this. First, we check, we know that the indexes are the same, so we're good. So we can use the product property. So we're going to put everything under 1 square root. And so we're going to do 72 times 10 times x cubed times x is x to the 4th, and y squared times y cubed is y to the 5th. Okay, so some of you want to go ahead and multiply 72 times 10, but remember, we're going to have to simplify this. So rather than multiplying everything together and then trying to factor it out, let's go ahead and put it in its factored form right now. So 72 is 9 times 8. So 9 times 8, well, but 8 can also be written as 4 times 2, and then 10 can be written as 2 times 5. So now we have 9 times 4 times 2 times 2 times 5 times, and then x to the 4th is going to be okay because we're going to be able to take that out with no problem. But if it helps you, you can go ahead and write that as x squared squared. So you know that when you take the square root, you're undoing that square. And then y to the 5th, that's going to cause us a little bit of problems. So let's write it as y to the 4th, or you can write it as y squared squared times y. Okay, so let's look at what comes out. So the square root of 9, of course, is 3, and then the square root of 4 is 2, and then the square root, where we can use parentheses, that way we don't get messed up. Okay, the square root of 2 times 2, of course, is 2, and then the square root of 5 is going to be an irrational number, so we're going to leave that in. Then we have the square root of x squared squared, so that's going to be x squared, but we have an even index, so we're going to put that in absolute value signs. And then the square root of y squared squared is y squared, and then, of course, y is just going to stay in the radical. So we end up with the square root of 5y. And now we can simplify. So 3 times 2 times 2 is 12. X squared and y squared are never going to be negative, so we really don't need the absolute value there. We can leave that like that. And then the absolute value of, or sorry, excuse me, the square root of 5y. Okay, go ahead and try this. Pause the video. Okay, welcome back. Here is your answer. Pause the video if you want to check. We can also do this with quotient rule. So the quotient rule says, again, the indexes have to be the same, and then we can write it under 1 square root. So really we can write this as the square root of 18x to the 5th over 2x cubed. And so when we simplify that, we have the square root of 9x squared, which is 3, and then the square root of x squared, absolute value of x. Same thing with cube roots, even when it's the same, so the index is the same, so we can rewrite this as the cube root of 162 divided by 3 is 54. And then y to the 5th divided by y squared is y cubed. Okay, so 54 is 27 times 2. So I can rewrite this as the cube root of 27 times 2 times y cubed. And so I know that 27 can come out because that's 3 cubed. So that's going to be 3. And then 2, we're not going to be able to take the cube root of that. And then y cubed, we can take that is 3. And so we left with the cube root of 2 under the radical sign. And since the index is odd, I don't have to worry about taking the absolute value. Okay, so go ahead and try this. Unpause the video when you're ready. Okay, welcome back. Here is the answer. And let's try another problem. So we can combine radical expressions by the product property or the quotient property. And the product property tells us that if the indexes are the same, then we can rewrite the nth root of a times the nth root of b as the nth root of a times b. And the quotient rule is very similar. If we have the nth root of a divided by the nth root of b, we can rewrite that as the nth root of a over b. We have to make sure a and b are real numbers, of course. Okay, we can also combine binomial radical expressions as long as the same index and they have the same radicand. So for example, if we have a nth root of x's and b nth root of x's, then we have a plus b nth root of x's. Same thing with difference. If we have a nth root of x's and we subtract b nth root of x's, then we have a minus b nth root of x's. And this is basically the distributive property because you have the same factor here that we're basically distributing out, and so then you're left with the binomial in the middle. Okay, so how can we do this? Well, when we look at A, we notice that the radicands or the indexes are the same, right? They're both square roots. And then we know that the radicands are the same. They're both 5x, so that's good. So now we look at, we have 3 square root of 5x minus 2 square root of 5x's. So 3 minus 2 is 1. So this is just 1, or 3 minus 2 square root of 5x's, which is 1 square root of 5x, which we don't bother writing the 1, it's just the square root of 5x. Okay, how about this one? Well, in this one, we notice that the indexes are the same, so that's good. However, the radicands are different. So, since the radicands are different, we can't combine them. Here, we look and the radicands are the same. However, the indexes are different. One is 3 and one is 5. So because the indexes are different, we cannot combine the expressions, and we just have to leave them as is. Okay, I want you to go ahead and take a look and see if you can simplify these. There are the answers. Okay, so what's the simplest form? When we look at something like this, and go ahead and ignore the you try for a moment, if we look at this, we notice that the indexes are the same, so we're halfway there, but the radicands are different. We might be able to simplify so that we have the same radicand. So I notice right away 250 is 125 times 2. That's 125 times 2. And 54 is 27 times 2. And 16 is 8 times 2. And 125, 27, and 8 are all perfect cubes. So I can simplify these individually. So first, let's look at this. So if I think of this as the cube root of 125 times 2, the cube root of 125 is 5. So I can rewrite this first term as 5 times the cube root of 2. And then the next term, I can rewrite the cube root of 27 as 3 cube root of 2. And 8 is, of course, 2. The cube root of 8 is 2. So minus 2, so minus 2 cube root of 2. And now I have all of my indexes the same and all of my radicands the same. So I can use the distributive property, so now do 5 plus 3 minus 2, all times the cube root of 2. And 5 plus 3 minus 2 is, of course, 6. And so your answer is 6 cube root of 2. Okay, go ahead and try the you try. Unpause the video when you're ready. Welcome back. Okay, there's the answer. Now, it doesn't just stop there. Just like we know we can do FOIL and distributive property, we can do the same thing here. So now, since we have two binomials that are being multiplied to each other, we can multiply the first term by the first term. So 4 times 3 is, of course, 12. And then we have the square root of 3 times the square root of 2. So we could put that in one square root as 9. Then 4 square root of 3 times 6, so minus 4 times 6 is 24, square root of 3. Okay, so then next up we have the next term, and so 5 square root of 2 times 3 square root of 2 is going to be plus 15. The square root of 2 squared is times 2. And then to wrap all of that up, we end up with the square root of, or 5 square root of 2 times negative 6, which is negative 30 square roots of 2. Okay, so let's combine like terms. Well, I don't have any similar radicands, and I have no way to simplify them any further. And then I have a constant. So I'm going to write this as 15 times 2 is 30, plus 12 square root of 6 minus 24 square root of 3 minus 30 square root of 2. Okay, so there is our most simple form of that expression above. Okay, let's try one more. So again, we have two binomials that we're multiplying together, right? So we have this binomial times this binomial, and we know how to multiply binomials. We're going to distribute each term to the other term. So 6 times 6 square root of 3 times 2 square root of 5. So 6 times 2 is 12. And then since the radicals are the same, 3 times 5 is 15. So we're going to take the square root of 15. Okay, and then the next, so 6 square root of 3 times 4 square root of 2. So plus 24 square root of 3 times 2 is 6. And then next, we have negative 5 times 2 square root of 5. So that's minus 10 square root of 5. And then we're going to multiply by the last. So negative 5 times 4 square root of 2 is negative 20 square root of 2. Okay, so now we look at all of the radicands, and we notice that 15, 6, 5, and 2, none of those can be reduced. So we're just going to go ahead and leave it as 12 square root of 15 plus 24 square root of 6 minus minus 10 square root of 5 minus 20 square root of 2. Okay, go ahead and try this one. When you're ready, unpause the video. Okay, welcome back. There's your answer. Okay, so you noticed in that last one that when we multiplied those two together, we ended up with a integer number, a real number, a real rational number. And so that idea of conjugates that we've talked about in polynomials is going to come back. And that's how we're going to what we call rationalize the denominator, which is get whatever radical there is in the denominator out of the denominator. So the conjugate here of the square root of 5 minus 1 would be the square root of 5 plus 1. And so if we want to multiply the bottom by the square root of 5 plus 1, we also have to multiply to the top, which may make the top more complicated, but that's okay. So we're going to do 2 times the square root of 5, which is 2 square roots of 5. And then we have 2 times negative 1, which is plus 2. Okay, so now that that happened, we look at the denominator, and we notice that the denominator is basically two polynomials, and we've dealt with that before. So the square root of 5 times the square root of 5 is going to be 5. Then we have the square root of 5 times 1 minus the square root of 5 times 1. Well, then that's just going to be 0. And then our final answer, negative 1 times negative, or positive 1, is negative 1 cubed, or just negative 1. Okay, so now we can simplify like terms. We notice everything here is going to be divisible by 2. So we have 2 times square root of 5 plus 1 over 2 minus 1 is 4. And so if we take out the 2, the common factor of 2, so this is 2 and this is 1. So now we can write that the square root of 5 plus 1, so that's the square root of 5, plus 1 over 2. Okay, let's try this one more time. So again, we want the conjugate that's in the denominator. We don't care about the numerator, and we're okay if that becomes more complicated. So the conjugate here would be the square root of 3 plus the square root of 5 over the square root of 3 plus the square root of 5. Okay, so in the numerator, right, we have 2 square root of 7 times the square root of 3, which is going to be 2 square roots of 21, and then plus the square root of 5 times 2 square root of 7 becomes 2 square root of 35. And in the denominator, we're going to multiply square root of 3 times the square root of 3 is going to be 3. And then when we do square root of 3 times the square root of 5, that's positive square root of 15 minus the square root of 15, so that's going to be 0. And then the square root of 5 times the square root of 5 is negative 5, because negative times a positive is negative, so that's minus 5. And so now we can take out a 2 in the numerator, so 2 times the square root of 21 plus the square root of 35, all divided by negative 2. And so we can divide out a negative 2 because that's a common factor. And so we end up with the square root of 21 plus the square root of 35 all over negative 1. And so we can rewrite that as the negative square root of 21, I don't know why I wrote 7, minus the square root of 35, because I just distributed that negative. Or you can also write it as the negative square root of 21 plus the square root of 35. That's also fine. Okay, go ahead and try this one, and unpause the video when you're ready. All right, there's your answer. Okay, so in general, if you're simplifying a radical expression, the index n should be as small as possible. The radicand contains no factors other than 1 that aren't nth powers of an integer or a polynomial. So if you're taking the square root, you don't want anything that can be written as x squared. The radicand should contain no fractions, so we don't want to have the square root of 1 over 3 hanging out. We need to write that as 1 over the square root of 3 and then rationalize that denominator. No radicals should appear in a denominator. So, like that said, you're going to multiply by the square root of 3 over the square root of 3 and end up with the square root of 3 over 3. Okay, so for more examples, go ahead and watch some more examples video. Otherwise, go ahead and complete the 4.3 reflection. Up next, we're going to talk about some rational exponents.